So I'll be talking about the Navier-Stokes equations in 3 space dimensions, essentially. The incompressible homogeneous Navier-Stokes equations. Okay, so basically this is a joint work with Gerard Bahouri from Paris 12 and Jean-Yves Chemin from Paris 6. And so I'll start this talk just by recalling a tiny bit about the Cauchy problem about Navier-Stokes, although I'm sure all of you know that very well, but just to fix ideas, okay? And then I'll try to tell you about some results we've obtained rather recently. So let me start with a brief introduction on the model. So I'll call U the velocity field of the fluid. And so the Navier-Stokes equations, as you all know, right like this, where I've taken a viscosity equal to 1 because it won't move for the whole talk, so I'll just take it equal to 1. And the divergence of U is 0. Okay, so that's the usual Navier-Stokes system. For the whole talk, I'll be in the whole space. Okay, so it's not just for technical, I mean, I really need to be in the whole space. It's much too hard to be in bounded domains, as you all know, domains with boundary. So I'll just work in RD, okay? And D will be 2 or 3, mostly 3. And okay, one thing I'll also do immediately is get rid of the pressure by projecting the equation onto divergence-free vector fields. Okay, so I'll call P this projector. Something like that, okay. And I'll apply this operator to the equation. And the last thing I do is by the divergence-free assumption on U, you can pull out the derivative. And P commutes with the Laplacian because I'm in the whole space. So this is the equation I really want to look at. Okay. So this is the Cauchy problem. I give myself U0, and the question is, am I able to construct U? If so, for how long? In time, is it unique? Is it regular? Okay. So I'm really interested in the Cauchy problem. So I hope I won't need this board anymore. It's much too high now. So. Okay, so this will just stay there as just the equations. So the Cauchy problem, I give myself some U0. And I'd like to construct a solution U. And I'd like U to be unique, and I'd like to know for how long I can do that. Okay? So one way to do this, which is probably the most traditional way to solve the equation, is to apply a fixed point theorem. Meaning I replace this equation by its integral form. So I have the heat flow applied to the initial data, and then I have some nonlinear term. Okay, and the nonlinear term is, of course, the following. You simply integrate the nonlinear part of the equation after applying the heat flow. Okay, so the question is there a fixed point to this equation which sends the right-hand side to U? So to do that, what you need to find, so I want to solve this, I want to find U as a function of time and space. Okay, and time, capital T, could possibly be finite, I'm not sure yet. So what I need to find to be able to apply a fixed point here is some Banach space of distributions, which I call X sub T, distributions living on 0T times RD, okay? And what I'd like is for B to be bilinear, sending xt times xt to xt. Okay, so I'm looking for such a space. And if I have that, then, as you all know, all I need to check is that if I apply the heat flow to U0, I compute that in xt. If this is small enough, meaning 1/4 times the norm of B, okay, then I know I can solve U uniquely in xt, at least in the space of functions whose norm is smaller than twice, for instance, the initial data. Okay? So all you need to do actually is to find such a space. Okay, if you have such an xt, then you have a solution. So what kind of spaces work? Well, one thing you could also try to do, which seems reasonable, is to find also a space for the initial data, right? I mean, xt is interesting, but what you want to know is where the initial data is, right? So you could also, looking for x sub t, you should also look for x sub 0, which would be the space of initial data, such that if my initial data is an x0, then the solution, or the heat flow, is an xt. Okay, so what I'd like to do is find both, right? I want to know where the initial data is. Okay, given x0, I find xt, which is such that the bilinear form is continuous. And then I'm done. Okay, so if you have such an x0, you can make a few comments. First thing you can say is that if my u0 is an x0, and if it's small enough, so I take u0 and x0 very small, then the heat flow here in xt will be also very small. Okay, so this will hold, and so I'll have a unique solution. Okay. Now, what does very small mean? Of course, it depends. Okay, and one thing which is very important, in my opinion, when you want to apply this kind of a method, is that if you want to make sense of smallness, the spaces in which you work with should be scale invariant. Okay, meaning, as you all probably know, this equation here has a scaling. Okay, so this will be important for the whole talk. So the scaling of the equation is the following. If you replace the initial data by, for any positive lambda, this initial data, so lambda is any positive number, and x0 is any point in Rd, well then the solution, if you have a solution associated with u, then this solution will be replaced by this scaling, which is exactly the heat flow scaling. Okay, so you have the same profile u, and it's just dilated exactly like u0. And that's the only scaling you have for Navier-Stokes. You can't change the powers around. That's the only one, right? Okay, so it's important that the norms in which you work here are invariant through that transformation. Because if they're not, you can just transform the initial data to make everything small, and then everything's fine. Okay, so it doesn't seem reasonable. So it seems reasonable for every function space I work with to be scale invariant. Okay, for instance, so I want, for instance, u0, x0 to be such that if I call u0 lambda, this lambda x0, this function here, then I want its norm to be invariant. Okay, so maybe examples of such spaces. Well, probably the easiest example would be in dimension d, the space LD. Okay, this is obviously scale invariant. So that you could ask the question, if my initial data is in this space, LD, can I construct a capital XT and make everything work? Okay, so the answer is yes, and actually there are lots of spaces which would work. Okay, so which is a problem in some sense, because if you have an infinite number of spaces in which you can try to make this work, you have an infinite number of theorems to prove, and it's tiring. So, okay, so one question could be, is there a best space in which you can do this? A larger space, okay, which would be the end of the story in some sense. So the answer is yes. So that's a proposition which is due to Yves Meyer, I think, at least in his book, and I'm not sure about the year, so I won't tell you. So the result is the following. So it's actually very easy to prove. It says that if you take any Banach space x0 of temporal distributions, and which is invariant, okay, meaning exactly this here, okay? Okay, so the norm doesn't change if I translate or dilate the functions in this way, then x0 must be embedded in some space, which I'll call b infinity, where the norm of a function u0 in b infinity by definition is simply the following. You take the heat flow, you apply it to your u0, you take the sup norm in space, and then you take some power of time. You have no choice about the power of time because it's just a scaling that tells you what you should put here. And then you take a sup in time. Okay? So that's not very hard to prove. I can show you if you're interested. It's really quite easy, actually, although it's surprising in some sense. First time you see it, you wonder why that's true, because it just tells you have no assumptions almost, just this one, right? You're invariant by scaling, and then you know you have to be in this space. Okay? So that means that's a good space for Navier-Stokes. That's where you should solve the equation. Because if you solve it in this space B infinity, then you've solved it in any space which is scale invariant. Okay? Now there's some bad news, which is due to Bourgain and Pavlovich in 2008, that says that Navier-Stokes is ill-posed in that space. Ill-posed means essentially that the map, the flow map, is not continuous in that space. Okay, which doesn't tell you Navier-Stokes is a bad equation, it just tells you that space is a bad space. Okay, so you shouldn't work with it. Right. So it's not too good news because it means you'll never be able to solve in that space. Okay, but what we know, so that's results proved much earlier by Cannon, Meyer and Planchon. So much earlier, 94. What they prove is that replacing L infinity here by any p does the job, any finite p. Okay, so they said if you take U0 in BP, okay, where this norm is simply, you take the heat flow again, right, and you take a power of time, and then you use scaling, and because of scaling it has to be this here, then you take the soup in time, okay. So what I said is that they take U0 in that space. If it is small enough, okay, then you can construct a space xt, which I won't give you, okay, and actually xt will not depend on t, because since this is small enough for any t, then actually you can take x infinity here, and you have a unique solution. Okay, those constants do not depend on t. So if this is small enough, this quantity is small enough, then you have a global unique solution. So that was their theorem. If U0 is small enough in BP, then you have a global unique solution in some space, x infinity I won't detail. Okay? Now what happens if U0 is not small? Well, if U0 is not small, then you can't use this inequality. Okay? So you have to go directly to this one here. And you ask yourself, is it possible for U0 not to be small, but still for this quantity to be small? Okay? So the only thing you can play with is t here now. Okay? Maybe if you construct your xt in some way, then for capital T small enough, this norm will be small. And then you'll have a solution in xt. Okay? So this does not work in BP, as far as we know, for the reason that, well, the reason for which we can't make it work in BP is that smooth solutions are, smooth initial data are not dense in BP. Okay, and you need to make this work, you need some kind of density. So what they did was to replace BP by some other spacers slightly smaller. So what you do here is simply the following. You still take this norm, but you replace the soup norm over t by an integral norm. Okay, so you take an LQ norm in time, then you want this to be still scale invariant. I haven't changed this power here, so to be scale invariant, you should put this measure. Okay, I won't be using definitions here, but I just give you the norms, and then so Q, of course, is finite here. Okay, so the theorem is if U0 is in this space, okay, which is smaller than that one, slightly smaller, then whatever its size, you have a unique solution for some small time interval. Okay? And of course, for the moment, T is finite. Okay, no one knows whether T is global or not. So of course, the next question is, can we make T infinite? Is it possible to take U0 in that space BPQ and prove there's a unique solution which actually would be global? Okay. So if you want to do that, you have to go beyond the fixed point in some sense. You have to know that for some reason, for instance, the norm in which you do your fixed point is bounded for some reason. which is given to you for some other reason, right? It's not just a fixed point. You need to know that the fixed point argument, you can push it as far as you want. Okay? So the question is, do you have information available on the equation of some bounded quantities? Okay, some norms which are bounded for some other reason. Well, the problem is there's only one conserved quantity that we know of, which is the energy. Okay, in any space dimension, if the initial data is in L2, then the solution should stay in L2 for all times. Okay, to prove that, you need to use the structure of the equation. You need to use the fact that if you do a cross product of this thing here by u in L2, you get 0. Okay, and because of that, the L2 norm remains bounded for all times for the solution of Navier-Stokes. Okay, but the problem is that L2 doesn't have much to do with those BPQ spaces, except in dimension 2. You see in dimension 2, the space LD of RD is exactly L2 of R2. Okay, and actually I didn't say that, but LD of RD is actually smaller than all those BPQ spaces, at least if P is smaller than D. Okay. So you can also, of course, prove a fixed-point theorem in LD of RD, right? But the best results we know basically are in those BPQ spaces. There is also another result, maybe I should mention also, by Kohan-Tataru, which is probably the best result we can hope for. So I won't state the result precisely, but they were able to prove that if U0 is in B infinity plus something else, okay, so which I'll precise a little bit, small enough, then you have a unique global solution in some space. Okay, so they need something else. We know it's not true in B infinity, because it's a theorem by Bourgain-Pavlovich. Basically what they added is that the heat flow applied to U0 should be an L2 loc in space-time. If you put this information and scale invariance, this gives you a norm called the BMO-1 norm, which I won't be using, so I don't want to define it here, but that's the best result you can prove for Navier-Stokes, probably. Okay, which is true in any space dimension. So it's almost B infinity, some other information you need, which is very natural. Just if you want the fixed point to work at the first step, you need this assumption. Okay. So that I won't be using, but just to go back to this, this here, you see that in dimension 2, L2 of R2 is scale invariant, and it's conserved, so you can prove there's a unique global solution for any U0 in L2. Okay, and that was known since Luret in the 30s. Okay, so in dimension 2, everything works well in the energy space, and actually, even if you take U0 in a BPQ space, it's also true. Okay, even if it's not small, the fixed point works for a small time, but then using the energy estimate, you can still prove the solution is global. So that's something we did with Fabrice Planchon. Okay, for finite Q. Again, you need smooth functions to be dense in this space to make the argument work. So in dimension 2, basically, you know you have a global solution, whatever the initial data. Okay, and actually it's even true in the Kohan-Tataru space, at least if you take the closure of smooth initial data. And that's a result by Pierre Germain. Okay, so in 2D, you know how to, you can solve the equation globally, whatever the initial data. And of course, the question is, in 3D, what happens? Under what conditions can you prove that the solution is global? So the problem with everything I told you up to now, except for the 2D results, is that they're true for any initial data, any equation, basically, which looks like Navier-Stokes. Meaning, you take the heat equation and you add some nonlinear term, which is bilinear with a derivative somewhere, then all those results are true, right? Whereas these here really rely on the energy inequality. So they really rely on the equation, right? And as you know, if you don't use the structure of the equation, then probably you're going to have a lot of trouble to prove, if you want to prove global regularity for Navier-Stokes, you're going to have to use the structure of the equation, right? You probably know the recent paper by Terry Tao, which says that you can construct an equation which looks like Navier-Stokes, which conserves the energy, and still you have a blow up in finite time. Okay, so you really have to be careful about the structure of the nonlinear term. Not only even conserving energy, you need to use more. Okay. So anyway, so today what I'll try to do is, if possible, using the structure of the equation, try to go a bit beyond what we know on Navier-Stokes. So the question is, what can we say on the initial data to guarantee you have global regularity? So some things we know, for instance, is that you have global solutions if, for instance, you perturb, so I'll call global initial data. Okay, what I mean is initial data giving a global solution. If you take initial data giving a global solution, you perturb it a little bit, then the solution is again global. Okay, whatever the size of this initial data. So that's a result by myself, Drago-Shiftinier, and Fabrice Planchon. So the set of initial data giving a global solution is open. Okay. Another way you can construct global solutions, which we'll be using in the following, is if you take, for instance, an initial data with two components only. Okay, so divergence free in the horizontal variables, and you make it depend slowly in the third variable. Okay, you put a small epsilon. Okay, so I was very worried with the subtitle of the conference because there is no limits in what I'm doing, but here I have an epsilon, so I'm relieved. Okay, so that's something we did with Jean-Yves Chemin. Okay, 2010. What we proved is that if epsilon is small enough, then this initial data, whatever its size, gives you a global solution. So you can check that this is not small when epsilon goes to 0. It's uniform, it's the same size as this profile here, basically in B infinity. Okay, the epsilon doesn't have anything to do with the norm. So this can be as large as you want, and still you have a global solution. Okay, this is not really a big surprise, because what you do to prove this is that you assume your solution looks exactly in the same way. Okay, so I'll call x sub h, h for horizontal, x1, x2. Okay, so you assume your solution looks like that. You plug this ansatz in Navier-Stokes, okay, assuming that this satisfies the 2D Navier-Stokes. Okay, so of course this whole thing does not satisfy the 3D Navier-Stokes equations, but the only mistakes are derivatives in the third variable, and any derivative in the third variable has an epsilon in front of it, so it's small. Okay, so of course you have to make this work, but the idea is this. And then with Ping Zhang, this we'll be using also in the end of the talk, we took this initial data here, I can call u0 epsilon, and we added any global initial data, V0. Okay, and what we proved is that if this slowly variable initial data vanishes when x3 is equal to 0, okay, so that's really a 2D part, then this is also global. Okay, so you take any initial data giving you a global solution, whatever its size. You add any profile which varies slowly in some direction. Okay, then for epsilon small enough, the whole thing is global. Why is that? Maybe I should explain this a tiny bit. Well, again, the idea is to guess what the solution would be. And so the guess is, I'll take the global solution associated with V0. I call that V. And then I take this solution here. Okay? And I want to say this is a solution to Navier-Stokes. Of course, Navier-Stokes is nonlinear, so it can't be true. So the question is, what mistake have I made if I plug this into 3D Navier-Stokes? Okay? So of course, the only mistakes are things like this, basically. Okay? Nonlinear terms with products, let's say, of V and U0 and U epsilon. And why is this small? Well, if you look at the solution here, you see the initial data is 0 at x3 equals to 0. So the solution is also 0 when x3 is equal to 0. That's wrong, but it's not very wrong. Okay, so that means the support of this is for some x3 between, let's say, 1 over epsilon and 2 over epsilon. Why? Because solutions in Navier-Stokes are compactly supported in space. That's also wrong, but it's not totally wrong. Okay, so this guy has a support in x3 which is very far, okay, whereas this is just a fixed solution. So its support in x3 is fixed in some sense. Okay, it's nothing to do with epsilon. Okay, so if epsilon is very, very small, these functions just don't see each other. And so that's the reason. Okay, so you have to work a little bit to make that work, but that's the general idea. Okay, so now the question we want to address today is a bit different. Okay, so what we've seen is that the set of initial data giving you a global solution is open. The question we asked with Gerard and Jean-Yves is the following. Is it open in the sense of weak convergence? Meaning, if I take a sequence of initial data, okay, so sequentially weak convergence. Okay, so I take this, converging in the sense of distributions to some u0. If I assume this u0 gives you a global solution, then is it true also for the sequence itself? Okay, so we know it's true for strong convergence in scale invariant spaces. Okay, that's what we proved with Dragos and Fabrice. Now the question is, if you replace strong by weak, is it again true? Okay, so of course, if you wanted to answer this question, you first look for examples and see if you can do it on examples. So the easiest examples are taking u0 equal to 0. Okay, so you take a set of initial data, converging weakly to 0. Does it give you a global solution? So one example, for instance, would be something like that. You take initial data, okay, v0, and you take this initial data. This clearly goes weakly to 0. So if what I want to prove here is true, then this gives you a global solution. And then by scaling, v0 also. Okay, because that's exactly the scaling of Navier-Stokes. So, okay, this is not what we're going to prove today. So this is a problem, right? If I can prove my result, then I can prove any initial data gives you a global solution, which I don't know. Okay, another example would be you take again a fixed profile and you take a translation. Again, this goes weakly to 0. If I can prove this gives you a global solution, then by translation invariance of Navier-Stokes, so does v0. So again, that's a problem. Okay? So what I want to do is state a theorem that tells you I take any sequence converging weakly to 0 except for those, and then it works. Okay? So now the question is, what does except for those mean? Okay, so you have to define a notion of convergence that says, I converge weakly, but I don't want to be scale translation invariant because this is just too hard. Okay, so the definition of convergence we're going to use here is rescaled convergence. Which means that I'll say that some sequence, okay, even of functions or divergence-free vector fields converges in a rescaled way to u0, which I call R converges to u0 if whatever sequence of positive numbers, whatever sequence of points in Rd, if I take lambda n of u0n minus u0, I rescale and I translate, this should converge weakly to 0. Okay, so not only this sequence converges weakly to 0, just take lambda n equal to 1 and xn equal to 0. Okay, so I have traditional weak convergence in sets of distributions, but also I need this to be true for any rescaling translation of my sequence. Okay, so maybe we should see some examples to see what that means. So for instance, if I take my n v0 of nx, what does it mean for it to converge, to R converge to 0? Well, if I use this definition here, take xn equal to 0 and lambda n equals 1 over n, I see that v0 must be 0. Okay. Okay, it's the same thing for that one, right? Just take xn equals minus xn or something. And again, you find 0. So if I take initial data which R converges to 0, it excludes, by definition, those profiles here. Okay? In some sense, only those profiles, which I'll try to explain later on. Now, are there interesting examples, or is just everything 0? So if I take, for example, the U0 epsilon I gave before, let's see, if I take, I'll just, okay, it looks a little bit like that. I'll take my first example here. Okay, and I decide to rescale only the horizontal variables. Okay, and I assume this R converges to 0. Is that what I want to do? Yeah, for instance. What does that mean? Well, you see this converges weakly to 0, except if I take this definition, if I take lambda n equal to 1 over n, okay, in that case I'll find something like this. Okay, take lambda n equals 1 over n. You get this. And for this to be true, you need V0 at point 0 to be exactly 0. Okay? Which is basically this assumption here. Okay? So we'll be using that probably a bit later on. So, okay, so this is a non-trivial example, right? This is not zeros. I'm just asking for V0 to be 0 when x3 is 0. So it's a non-trivial example, which works. So the theorem I want to prove is that if I have a sequence of divergence-free initial data, which R converges to 0, which is global, then my sequence is global. Now, before doing that, I need to say in what space this is bounded. Okay, I'm saying I have a sequence. Where is it bounded? It R converges to something. In what space is it? So this is not so obvious. So in what space should I take my initial data to make the theorem work? Well, for instance, if you take one initial data I'd like to see in this result would be initial data like this, right? Because that I know is true because of another theorem. Okay, so I'd like my theorem here to be true for this class of initial data, for instance. Okay. Now, in what space is this bounded? Well, for instance, if you compute, I'm in dimension 3 here. If I compute the L3 norm of this initial data, what I get is n 1/3, which is not bounded. Okay, so the notion of R convergence, in some sense, excludes the usual scale invariant spaces. Okay, I can't say I take initial data bounded in L3, which R converges, because if I do, I miss out that kind of initial data, which I'm interested in. Okay, so I have to try to move out of the usual L3 BPQ spaces. So how should I do this? Well, you see this initial data here is special in the sense that I'm not counting derivatives in the same way in the horizontal and vertical variables, obviously. Okay, so what I should take for spaces for the initial data, for instance, for this or for that one, would be L2 in horizontal variables, and for instance, L infinity in vertical ones. That's a scale invariant space. You can check that, because L2 of R2 is scale invariant. Okay, and that is a good space for all those families of initial data. So that's where I should take my initial data. Okay, the problem with that space is that the first thing you want to do is to be able to solve Navier-Stokes at least for a small time. Okay, and I have no idea if you can solve Navier-Stokes in this space. Okay, L infinity is not so nice. Okay, so the natural idea is to say, okay, let's just replace a tiny bit this space and put more natural norms, which would be Sobolev norms. Okay, homogeneous Sobolev norms. Okay, that's better in the sense of Navier-Stokes. Still scale invariant. The problem with this norm is that, well, the space is that it's not normed. H1 in dimension 1 is not a nice space. Okay, so still we weren't very happy with that space. So we thought, what's the closest space to H1 in dimension 1, which is a nice normed space? And there the BPQ spaces arrive. So you can take a slightly smaller space, which is the BPQ space in dimension 1. Okay, I won't give definitions. Just take the BPQ spaces up here, replace D by 1. because I'm in dimension 1. This is a good Banach space. Sorry, not 2 here, because that would be equal. I want to put 1 here. Okay, B2, 1. Okay, you can prove easily that this space is included in L infinity, actually. It's an algebra. It's a very nice space. Okay, the problem with this space here is that L2 is, by definition, actually a B2, space, dimension 2. Okay, whereas this space is a B2, 1 space. Okay, I say Q equal to 2 in 2D, Q equal to 1 in 1D. This is not so nice if you want to do products, if you want to solve Navier-Stokes. So maybe we could do that, but we didn't want to because we're a bit lazy. So we replaced the 2 by a 1 here. Okay, and now we're almost done. The last thing we did, okay, again for technical reasons, which I won't have time to explain. So if you don't like those BPQ spaces, you can sort of forget what I'm saying right now and just stick with this space here. But if you're interested in actual norms, what we really did was solve the equation in B11 in any space dimension. Okay, that's technical, I won't tell you why. So it's slightly smaller again than, okay, it's not exactly that. So, okay, I won't be going into details of computation, so I don't need to give you, I hope, real definitions. But it's exactly the spaces I wrote somewhere up there. You take B11 in 2 dimensions, B11 in 1 dimension. This is a scale invariant space for Navier-Stokes, but you're measuring differently the horizontal and the vertical variables. That's all you want to know, I think, for what I'm going to explain anyway. And if you want to know what functions in that space look like, remember this example. This is the easiest. It's exactly the same space, except we put derivatives in different directions. Okay, so now I can state the result and give you an idea of how to prove it. Okay. So the result is the following. I take U0n, which is bounded. Okay, so I'll just call B this space here. B11. Tilde maybe. Okay. And actually I even need, again for technical reasons, the small q here to be smaller than 1. Okay, just forget that for the moment. It's technical, but imagine I'm just saying L2, L infinity, but in the BPQ sense. Okay, so I take this, I assume this initial data R converges to U0. I assume U0 gives rise to a global solution, to a unique global solution. And then the theorem says that for n large enough, so does U0n. Okay? So apart from, this is a bit messy about function spaces, if you take initial data, which is bounded in a space which looks like L2, L infinity, okay, assume it R converges to an initial data, which is divergence free, of course, and which gives rise to a global solution, then the sequence does also. Okay, that's the result. So just for the end of the talk, I'd like to explain a little bit about the proof, which relies on what's known as profile decompositions. So what I'll be using here is a theorem which was proved by Gerard in '96, which I'll explain right now, and then I'll show you how to adapt his theorem to our setting. Okay, so his result in a very particular case in dimension 3, he was studying how H1/2 of R3, which we know is embedded in L3 of R3, and he wanted to know in what way this embedding is not compact. Okay, why is it not compact? Because of the examples here, right? These sequences are clearly not compact. So his theorem is the following. If you take a sequence phi n, which is bounded in H1/2, assume it converges in the sense of distributions to some phi 0 in H1/2, then what can you say about phi n? Well, what you'd like to say is that phi n is phi 0 plus something small. Okay, so something small meaning psi n in L3 goes to 0 when n goes to infinity. Okay, if that was true, that would mean that the embedding is compact. Okay, so it's not true. So what you have to do is add something to phi 0 to make this true. What do you add to phi 0? Well, you add precisely things which are like R converging. So it's a sum of profiles with some scales, 1 over lambda n, some fixed functions phi j, some translations. Okay? And the theorem tells you that the more profiles like this you're able to extract from your sequence, the smaller the remainder is. Okay, meaning that when you take not n going to infinity, but j, then the remainder is very, very small. Okay, so that's not enough. You can't just say this. You have to explain a little bit what those phi j's are all about. So how do you find those phi j's? Well, simply what you do is that you rescale your phi n, and you translate it, and these things go to the phi j's. Okay? So you take your sequence, you descale it in some sense, and you get those phi j's. Those lambda nj's are orthogonal, meaning that if you take their quotient, it has to go to 0 or infinity. Okay, so they don't see each other. Right? They're very different, except if they're not. But if they're not different, then they're equal to 1. And if they're equal to 1, then the concentration points here should be very, very far away, one from the other. Okay? So you should understand each one of those functions, which look a bit complicated up here. There's some kinds of bubbles, as Précis-Couron said, right, which don't see each other. They're orthogonal. They're living at different scales, or if they are at the same scales, then those points are very, very different, very far from each other. Okay? In particular, for instance, if you take the h1/2 norm of phi n, you get exactly the weak limit, the psi n, which has no reason to be small, plus all those profiles, and because of scale invariance, you get exactly that. This means that they're really orthogonal. They don't see each other. If you do a product of two profiles, you get 0, basically, when n goes to infinity. Okay, so I think that's all I wanted to say about those profiles. So now, if I want to prove my theorem, what do? I take initial data, which is bounded in some space, okay? And I'm going to try to write it down as a profile decomposition. Okay? What's going to happen is I'm going to have exactly those profiles, except that since I have different regularities in the horizontal and vertical variables, I'm going to have different scales in horizontal and vertical variables. So that's a theorem we proved with Bahouri. Okay, that you have exactly the same thing. The norm here is a little bit different. Okay, and the epsilon and j's are just different scales. They also go to 0, 1, or infinity. Okay, so it's exactly the same theorem as Gerard. You're not bounded in h1/2. Okay, so I should remove that also. Okay, I'm bounded in my space B. Okay, then I have exactly the same decomposition as Gerard, except that my scales can be different in the horizontal and vertical variables. Okay, now I need to remember that I are converged to something. Okay, so let me say that I'm writing this just for the third component, for instance. Okay, so this is a function. I know that R converges to something. That means that if I remember this now corresponds to the case when if the epsilon j is equal to 1, I have exactly that. Okay, exactly because Gerard proved it. Okay? But because of R convergence, I know this has to go to 0. Sorry, that was phi minus the weak limit, sorry. That was a mistake, okay? I have to remove the weak limit. Then because of R convergence, by definition, this is 0. Right? The definition is here. Okay? So when I take this profile decomposition and I use R convergence, I'm killing all the examples I don't want to see, all the functions which really look like those here. So I write down the profile decomposition, and I know the scales are different in the vertical and horizontal variables. Okay, so now I know that the horizontal scale is lambda and j, and the vertical one is epsilon and j over lambda and j. Okay, so I'm almost done. Now I want to precise a little bit more what the vertical scale is. So to do this, I'm going to remember that my initial data, U0n, is divergence free. Okay, so I have this D3 U0n3, which is equal to minus the horizontal divergence of the horizontal components. Okay? Now, if U0n is bounded, let's say, to make things simple just for the computation, in L2 horizontally and H1 vertically, which is a little bit wrong, right? Remember, it's something else, Bezoff spaces. But basically for scaling, scaling-wise is the same. So U0n is bounded in this, so the divergence is bounded in this. Okay? So U0n3 is bounded in this. Okay, just the divergence-free condition is telling me that. Now if I take a typical profile here, something like this, I have a horizontal variable and a vertical variable. A typical profile should be bounded in this space. Okay? So let's compute this norm for this profile and see what happens, roughly. What I get is what? So I'll try to make this correctly. So I have lambda minus 1, which is here. I take minus 1 derivatives in the horizontal variable. That gives me a lambda. I take an L2 norm, which gives me, again, a lambda. Then 3 half derivatives in the vertical variable, and an L2 norm, which is minus 1 half. Is that okay? Yeah, that's okay. What I get is epsilon. Okay? Now I know each profile should be bounded in this space, and its size is epsilon. So epsilon, which goes to 0 or to infinity, has to go to 0. Right? All those scales epsilon. And if they go to infinity, I don't have something bounded. Right? So what I'm saying here is that in this decomposition, I only have small vertical scales. Okay? And that I know how to solve because of those theorems here. Okay? So because of our convergence, I know that horizontal and vertical scales are different. Because of divergence-free conditions, I know each profile typically is someone like this. Sorry, someone like this. x1, x2, x3, with epsilon very, very small, going to 0. Why would this give you a global solution? Because of scale invariance, for this to be global, it's enough to prove that this is global. Right? Because of scale invariance. This I know is global, because we proved it with Jean-Yves a long time ago. So is this profile. So each profile in the sum has a global solution, and now all I need to check is that the sum is global. Right? But that we know how to prove because of the same results as this. When you take Navier-Stokes equation with initial data, which live in 2 different scales, the sum of the solutions is an approximate solution of the equation. Okay? So that proves, in some sense, that each one of these guys gives you a global solution, and so does the sum, and the theorem is proved. Thank you.
We have some time for discussion. Are there questions? You should use this microphone because of the filming.
Just a question. When you say global unique, you mean unique in your class, right?
Yeah, but then you can propagate regularity, actually. Okay. So what happens, okay, that's a very good question. When you take initial data in this space here, of course, the first thing you have to do is check you have a solution even for small data in that space, for instance. And what you prove quite easily is that your solution is an L2 in time with values in L infinity. And that's a uniqueness class for even for Loré solutions, actually. Mm-hmm. So they're unique in even weak sets, even with respect to weak solutions.
Okay.
Right. So, other question? Well, of course, the natural question is also usually, what about half space? No? So you mentioned in the beginning, the spaces are maybe not so suitable for half space problems.
Right.
And looking at this scaling or this decomposition in the horizontal part and the third component,
right.
Is there a way to work on the half space
Okay.
Or positive x3?
Okay, I could say probably, but I have no idea. If, okay. As long as you don't put any geometry, like a half space, maybe it works, yeah. When you start putting geometry, there are two problems. First, the set of initial data makes no sense. I mean, we've decided one direction is special. If your domain has no special geometry, it doesn't mean anything. And then even profile decompositions in domains are a bit strange. I mean, you have to understand what you're doing because the domain is changing with the profile. Right? So when you take a half space, there's no problem. But if you start taking a curved space, then your profiles live in a half space, typically. Right? So, okay. I can't really answer. I would guess it might work. I mean, you have to work on those function spaces and half spaces, but that has been done. So I would guess it would work, but I have no idea. I haven't tried.
And what about the splitting in all 3 dimensions? Different scalings for x1, x2, and x3?
Okay. Well, we're really using very much the fact that the 2D Navier-Stokes equations are well posed. Okay. The divergence-free condition. In three different scalings, I don't know exactly what you'd be able to use, right? Because the 1D Navier-Stokes equations doesn't make any sense. Incompressible Navier-Stokes equations. So, okay, I haven't thought about it, but I'm not sure I would be able to do something very interesting in that case. I'm not sure.
Okay, thank you. So are there other questions, remarks? This doesn't seem to be the case, so let us thank the speaker again.
Thank you.